We did the rotational version of kinematics, and it looked very much like the linear version of kinematics. We made some changes where we had x, v, a. We replaced these with theta, omega, alpha, and then we were able to pretty much use exactly the same things as we had before. The next quantity that we're going to look at is force, or the rotational version of force, torque. So this is a video about torque. Torque gets a lowercase Greek letter tau, and we are going to define this as a perpendicular force times a distance. Here's something that gets a little bit weird. This is units of force, this is units of distance. We get a Newton times a meter. Before, we equated that to a joule when we were doing energy. For torque, we actually just leave it as Newton meters. And it's mostly just because we don't want it to be confused with energy. So what is torque? Well, x became theta. That was an angular position compared to a regular position, linear position. We had an angular velocity compared to a regular velocity. That's how our position was changing over time. We had, once upon a time, linear acceleration is how our velocity is changing over time, and that became an angular velocity. Force was the thing that was causing the acceleration, so torque is going to be the thing, right? Force caused acceleration, so torque is going to be the thing that causes angular acceleration. Torque is the rotational version of force. This formula looks a little bit strange, but it should make some amount of sense. Let me do this. If I have the wheel of a car like this, and I want to change the tire, I might use a tire iron. I might get out my tire iron. So I get out my tire iron. Now, I stick my tire iron, my very largely oversized tire iron, onto the lug nut, and now I've got a choice. I've got to push this thing. I can apply force a couple different ways. I could apply a force here in this direction, but that force unfortunately isn't going to really make this thing turn. What I need is a force that's perpendicular to this bar. So if this is right here, my line, kind of my line of action, if you like, then what I need is a force that's applied perpendicularly to that. Now I can apply something diagonally compared to it also, but I've just seen that applying something parallel doesn't help me out any. Anything that's diagonal, I could break into a component that's parallel and a component that's perpendicular, and the parallel part I'm just kind of throwing away anyway. So what I would like to do is find a perpendicular force. If I wanted to apply my force here, that would certainly turn my bar. But if I took that same amount of force and applied it out here, it would be more effective. And you know this because if you have a door at your place, at school, at wherever you like, if you have a door and you really want to show, let's say, your excitement, not anger and frustration, and you throw that door shut, you're going to slam the door, right? If you're going to slam the door, you're not grabbing the door right near the hinge. In this situation, this is the hinge. You're not grabbing the door near the hinge and trying to slam it there. That doesn't do it. If you really want to slam this thing, you're going to grab it out at the far edge because your force is worth a whole lot more out there. The quantified version of why your force is worth more out there, that's called torque. So you have with this a distance from your axis. Now with anything rotation, with anything torque, with anything like that, all your measurements are relative to your axis. In this case, we have a hinge. Because we have a hinge, that's going to be the natural axis point. That's going to be the point where this door swings on. We are going to look at a distance from the axis, and then we're going to apply a force. And we could apply that force diagonally, so let me do that. Let's go with orange for the force. I could apply a force this way, and then I would break that force into two components. I've got one that goes this way, that's like my parallel force, it's parallel to this red line, and I've got one that goes this way, that is my perpendicular force. The parallel force does me no good at all, doesn't do anything, so my torque is going to be equal to the perpendicular force times d. If I have the angle between, then I could write this as like an FD sine theta sort of thing, but just like I did when I was looking at work, I would much rather define this thing in terms of perpendicular and parallel, because that's always true. So that's torque. That's kind of how it works and what it does. We will look at some examples of just what to do with it a little bit later. For right now, it's enough to say that the torque we apply is equal to the perpendicular force times the moment arm, lever arm, whatever you want to call that, times the distance from the axis. Torque is a vector, strictly speaking, but we don't really think about it in terms of vector. If this is a bar, and this bar has a length of d, and I apply my perpendicular force, let's say here, then that force is going to cause, if this is my axis, that force is going to cause the bar to rotate this way, counterclockwise. I would say that this force produces a counterclockwise torque. If I applied instead a force over here, downward, this force is going to induce a clockwise torque. Just like I wanted to be careful way back when about defining a direction as positive, I want to define a direction as positive here also. By default, we generally take counterclockwise to be the positive direction, but by that same default, we generally take up to be a positive direction and right to be a positive direction. It doesn't have to be a rule. It's just what you see the most often. The reason we want to think in terms of clockwise and counterclockwise is if I've got instead a bar like this and my axis is here in the middle, which could happen if I have, I don't know, like a fan blade or something like that that goes around. If I apply a force back here, up was a counterclockwise torque. So if I apply that same force here, and I stick with the idea of counterclockwise being my positive direction, then this is going to produce a positive torque. If I apply a force upward on this side, that one is going to supply a negative torque, because if that force were acting on its own, the bar would start to rotate in that direction. So I don't want to think in terms of up and down, I want to think in terms of clockwise, counterclockwise. Pick a direction to be positive, and then just stick with it. That's it. That's torque.